Hello and happy Monday. I hope you had a good weekend and are so far having a good day at school. Sorry that I'm not here today for 7th period, but I think this video, along with Mr. Blasky's help, you'll be able to go through the content just as if I was here. So today we are learning about section 2.5, completing the square. Now, completing the square should sound familiar to you as it's an algebraic process that you learned about in Algebra 1. Our two goals today are to make sure that we remember how to complete the square and also to figure out how we can apply completing the square to quadratic functions. So at the top of your paper, you will see that you have two warm-up problems. These are two quadratic equations that I would like you to solve. You'll notice one of them is in factored form and one of them is in vertex form. Please pause the video and spend a minute solving these two problems. All right, let's check and see how you did. So for the first one, I hope you used the zero product property. The zero product property works nicely when things are factored because each factored piece might equal 0. So I take each factored piece, I solve each one, and I get -2 and 4 as my solutions. For part B, because it was written in vertex form, I don't want to waste my time expanding and then factoring, so instead I chose to use what's called the square root property, which has me isolate the squared term so that I can eventually take a square root. So I added 16 to both sides. I took the square root of both sides, remembering that I need a plus or minus when I take the square root. That resulted in two equations, one that equaled 4 and one that equaled -4, and I found my two solutions, 3 and -5. So the real question becomes, these two problems were easy when they were written in factored form or vertex form, but what if they're written in standard form? Now, if I have something in standard form, I know that I can put it into factored form very easily by factoring, right? We did it all last week. If I want to go from standard form to vertex form, that's where this process of completing the square is going to come in handy. So let's go ahead and start talking about what completing the square is and remembering how to do it. All right, so what is completing the square? It is an algebraic process that lets us find a value of c that when added to the expression x squared plus bx creates a perfect square trinomial. So we will know the x squared term, we will know the bx term, and we want to try to figure out what is this value that I want to add in that makes this a perfect square trinomial. So the way that I'm going to show this is by drawing some pictures and using some tools that we've maybe seen in 3rd or 4th grade math. You might consider putting your pencil down and just watching, and once this part of the video is over, pause the video so that you can copy it down on your own notes. I'm going to draw some pictures to help me figure out what this c value is. I would suggest that you put your pencil down and watch what I'm doing, and once this part of the video is over, you can pause it and copy this down into your notes. So the first thing I'm going to do is create something that looks like x squared. And the way that I'm going to do that is I'm going to make a shape that is a square, and I'm going to label its sides as x and x, so that its area is x squared. The next thing that I'm going to do is I'm going to make a rectangle whose length is going to make up the b and whose width is going to make up the x. So all together, I'll get the area is the middle term, bx. So I'm going to choose to make the height be a length of x, and the length across is what I'm calling b. Now, b could be any number, so for now, we're just going to keep it as a variable. So the area of this rectangle would be bx. And my goal is to try to figure out when I add these two things together plus one more mystery thing, how do I create a square? So keep that in mind. We're trying to create a square. So the way that I'm going to do this is I'm going to actually try to make a square out of the things that I already have. Now there's going to be a piece missing, so we'll have to figure out what that piece is. So here's how I'm going to do it. I'm going to put the x squared square here. And I'm going to take this rectangle that was a bx square, and I'm going to split it in half. So I'm just going to cut it right down the middle so that this piece is now b over 2, and this piece is b over 2. The height is still x, but that's going to allow me to take half of it and put it down here. So notice its length here is still x, but now its height is b over 2. And I'm going to take the other one and put it over here. So again, this length is still x, this piece is b over 2. And what I notice is if I look at the areas together, I have x squared, I have a b over 2x, I have another b over 2x, and then I have this mystery spot at the bottom that if I were to add something in, that would be my perfect number to make this a square. So I'm going to use the areas that I labeled to figure out what is the area of this square. Well, this length I was calling b over 2, so it must be b over 2. And the length across the top must be the bottom length, b over 2. So the area of this piece that I want to add in must be b over 2 squared. So that is my value of c that I want to add in to my expression to make this thing a perfect square. So I could write it like x squared plus bx plus b over 2 all squared. Now, how is this a perfect square trinomial? Well, look at the square that we created. Its length across the top was x plus b over 2. Its height was x plus b over 2. So I could call that x plus b over 2 all squared. And I have now created what we like to call a perfect square trinomial. It's a perfect square trinomial because if I expand it, it's a trinomial, and I can also write it as a perfect square. We've identified what is this value of c that we need to add in, b over 2 squared. Let's go ahead and get some practice actually completing the square. We'll start off with some that are a little easy and we'll work our way up. So example 1, can we complete the square for each expression, and then we're going to factor it. So in order for me to figure out what this number is that I want to add in, I take the b value, which is this middle value, I divide it by 2, and I square it. Well, 8 divided by 2 is 4, 4 squared is 16. If I want to write this factored, I would call it x plus 4 all squared, which makes sense because this was the value of b over 2, which if we scroll up, that's exactly how we were writing our perfect square. Go ahead and pause the video and try parts B and C, and then we'll come back and check how you did. All right, so go ahead and check your work to parts B and C. On part B, the number that we wanted to add in was 9, and I would check to make sure on part B that your factored expression is x minus 3 squared. And the reason it's minus is because B was negative 6. Part C, you should have found the number you wanted to add in was a 1, and then your factored expression was x plus 1 squared. So now that we've figured out how to complete the square, let's actually get some practice in the context of a problem. So let's go down to example 2. We're going to work through part A together, and then I'm going to have you try part B on your own. So for part A, we want to solve the quadratic by completing the square and applying what's called the square root property. So what I like to do when I complete the square is I like to isolate the variables and get anything else to the other side. So I'm going to rewrite my expression by adding 3 to both sides. What I notice is that I want to create a perfect square. So this is where I ask myself, what number do I want to add in to make this side of my equation a perfect square? Now what you should remember is that I can't just add in something to an equation, otherwise I've changed the problem. So the way that I'm going to cancel this out is I'm going to add the same thing to the other side. I can add 1 to both sides of the equation, 5 to both sides of the equation. As long as it's to both sides, I haven't changed the problem. So now I get to complete the square. I take my b value, I divide it by 2, and I square it, and I get 1. So to counter that, I'm going to go ahead and add 1 to the other side. Now the whole reason why we completed the square is to write this left side as a perfect square. So let's go ahead and factor it. It factors into x plus 1 squared. The other side simplifies to 4. And now it looks almost like our equation was in vertex form, and now we can use the square root property. So I'm going to take the square root of both sides, so I get plus or minus the square root of 4. I know the square root of 4 is 2, so one of my equations should equal 2, and the other one should equal negative 2. If I solve the first one, I get that x is 1. That's one of my solutions. And if I solve the second one, I get that x is negative 3. So I used completing the square to rewrite my equation so that I could take the square root of both sides. So go ahead and pause the video and try part B. All right, let's check and see how you did. So hopefully you noticed this one was a little bit nicer to begin with. Your x terms were already isolated by themselves, so you didn't have to add that 8 to the other side. It was already over there. I completed the square by adding in 4. I did it to both sides to keep the equation the same. Now this one was a little bit different because we ended up taking the square root of negative 4. But now that we've learned about imaginary numbers, we know the square root of negative 4 is 2i. Because of the plus or minus, I also have negative 2i. I subtract 2 from both sides, and I come up with my 2 imaginary solutions. All right, we'll move on to part C, which is on the back. So on part C, the first thing that I notice that's different is I have a coefficient in front of my x squared term. Now I'm still going to start out the same way. I'm going to subtract 50 from both sides so that I can isolate my x terms. But now, before I go start completing the square, recall that completing the square had to look like x squared plus bx plus c. I wasn't supposed to have a number in front of the x squared. So I'm going to factor a 2 just from my x terms. I'm going to keep the negative 50 as it was. And now I'm going to go complete the square, keeping that 2 out front, reminding myself that if I'm adding something to one side, I want to add it to the other side. I go through and I complete my square, so the number that I want to add in is a 16. Now, I don't want to just go add 16 to the other side because I notice what I actually added in was 32. So I'm going to go add 32 to the other side. As I continue, I can go ahead and write this as a perfect square, so x minus 4 squared. I simplify negative 50 plus 32, which is negative 18. I divide both sides by 2, and I'm left with that same square root property that we've seen before. I take the square root of both sides. I get plus or minus the square root of negative 9, which now we know that's the square root of negative 9 is 3i. If I create my two equations, one of them gives me 3i plus 4. The other one gives me negative 3i plus 4. And there are my two solutions. All right, this last example has us trying to write the equation in vertex form by completing the square. So even though I have a y, I'm still going to isolate my x squared terms by adding 13 to both sides. I notice that my x squared has a coefficient in front, so just like the last problems that we saw, I want to factor out that leading coefficient. I only take it from my x squared terms, and I notice that because I took out a negative, that leaves me with a negative 4x. Now I get to go complete my square. I like to show myself that whatever I add into one side, I add into the other side. So I leave those spaces. It looks like those numbers I want to fill in must be a 4. But when I notice what I need to put into the other side is I really need to put in a negative 8 because that's what was put into the right side. If I keep simplifying, I rewrite this as a factored form, so x minus 2 squared. To get it into vertex form, now I just need to subtract 5 from both sides. Now the last part about this problem asks me to find the maximum or minimum value. The value is the y value, which I already know is negative 5. To figure out if it's a max or a min, I go look at the value of a, which in this case is negative, which means that the vertex was a maximum, so this must be my maximum value. I'm going to leave you to try part B, and Mr. Blasky will show you the answer. Have fun!